and so on. And in principle, such materials can help us improve existing hydrogen batteries. So it's interesting direction, quite new. Next direction is probably the most important. It's still the unsolved fundamental problem. It's a search for room temperature superconductivity. And one of promising way how to solve it, how to find the room temperature superconductor, is probably doping of yttrium hydrogen system. If we introduce, say, 5–15% of lanthanum inside of yttrium H10, maybe it's possible to stabilize a cubic modification at a little bit elevated pressure, such as 220–250 GPa. Another option is to synthesize cubic actinium H10. Come on. Yes. Fourth direction is a synthesis and search for high temperature superconductivity in ternary hydrides. At this moment, 3 systems were investigated and published. It's a lanthanum-yttrium hydrides, lanthanum-neodymium hydrogen system, and lanthanum-cerium hydrogen system. 2 groups from Jilin University published recently papers about this nice system. So what can I say about this? We aimed to increase the critical temperature of superconductivity in lanthanum-yttrium system, lanthanum-yttrium hydrogen system. Unfortunately, was not achieved. This aim was not achieved. When we added neodymium to lanthanum H10, we observed suppression of superconductivity in this system because neodymium is magnetic impurity, magnetic dopant. And in the last system, in lanthanum-cerium hydrides, the actors and my colleagues from Jilin University, they found that we can get some benefit in stabilization pressure. Stabilization pressure can be decreased because of formation of new hexagonal phase. But unfortunately, the critical temperature also decreased, and actually, we are going down with this system from 250, which is TC for lanthanum H10, to about 180, which is maximum TC achieved for lanthanum-cerium hydrides. Next direction was, let's say, opened by a group of Dubralinsky from Bayreuth University. They developed the single crystal X-ray diffraction methods for diamond cells, and we can now study the we can get the exact position of heavy atoms, and in some cases even hydrogen atoms in polyhydrides at high pressure up to 200 GPa at least. And recently was published very remarkable paper. It's Daniel Laniel, who studied high pressure synthesis, who investigated high pressure chemistry of lanthanum hydrogen system and found several new lanthanum polyhydrides. It was published in Nature Communication this year. So I think it's very promising direction. Next direction is the search not for room temperature superconductor, but for room pressure superconductor. Several interesting results were obtained via calculations, via DFT methods. For example, barium silicon hydrides and strontium silicon hydrides. We can say it's tetrahydrides were predicted by Lilia Baeri group in Italy, in Rome, as well as lanthanum boron H8 was also studied in this group, and some other groups also contributed to this discovery. And all of these compounds are quite stable. They are stable below 50 GPa and should demonstrate quite high superconducting properties. TC may reach 126 kelvins. I would like to say here that these 2 first compounds are much simpler to synthesize, much simpler to investigate, because a precursor for those hydrides can be synthesized at low pressure at 0 GPa, because barium silicide and strontium silicide, exact one-to-one stoichiometry, they were already described. They were already synthesized, and we can just repeat this synthesis, mix barium with silicon, heat the mixture, and get the precursor for consequent loading of hydrogen using, let's say, ammonium boron. Ammonium boron, heat barium silicium together with ammonium boron, and maybe we will be able to synthesize this barium silicium H8 or strontium silicium H8. And the last direction of research is theoretical. Theoretical computations, DFT approaches, And I would like to underline only two discoveries. I would like to focus on only two discoveries. It's clutterate structures. It's a lithium 2 magnesium H16 and cerium H18. The main problem of theoretical calculation is that we do not know will this table be stable, will those phases be stable in real condition, and reproducibility of such calculations are not always 100%. For example, I took for this room temperature superconductor at cerium H18, I took different pseudopotentials. I used Perdue-Zunger exchange correlation functional, and I used a tetrahedron integration to calculate the electron-phonon interaction coefficients for this compound at 400 GPa. And my result for different meshes, K and Q meshes, is about 140 kelvins only. So it's a very big difference. I couldn't repeat these calculations of the group of Yan-Min Ma calculations. I couldn't repeat. And it's one of the drawbacks the theoretical approach suffer from. Okay, as I would like to start my presentation from the discussion of recent experimental results. I have heard about this paper just maybe a couple of days ago. It was published on arXiv, a group from Institute of Physics, Chinese Academy of Science, recently investigated what will happen if we load a tantalum together with ammonium boron and squeeze it to 200 GPa. And after laser heating, they discovered that this compound, that new compound, forms. It's a tantalum H3, and this compound demonstrates a superconducting transition at just about 25 kelvins. Very low, pretty low critical temperature. I would like just to remind that for tantalum hydrogen system, it was predicted that at 200 GPa, several other phases should form, such as tantalum H4, tantalum H5, tantalum H6, and they all should have much higher critical temperatures that it was found in this experiment. The same group recently studied zirconium polyhydrides and found that TC of zirconium polyhydrides is just a little bit above 70 kelvins, and they studied hafnium hydrides as well and found that TC of those hafnium hydrides is also close to 80 kelvins. So what's important? We can compare theoretical predictions made in 2018-2020. You can see on this slide this colorful map. It's results of predictions. It's a maximum TC for different binary system, nickel hydrogen system. You see it's very colorful actually. Yttrium, lanthanum, strontium, calcium, magnesium should give high TC, scandium, zirconium, hafnium, thorium, iridium as well. But this is predictions, and now in 2022 we can say that island of high temperature superconductivity in nickel hydrides is actually very, very small. In reality, we do not have a wide choice. We have a calcium, yttrium, lanthanum, and thorium, and that's all. That's pretty all. All of these compounds, all of these metals form hydrides, polyhydrides with TC above 150 kelvins. But all rest elements, as I showed before, they do not give high temperature superconducting hydrides. The people made some kind of circle. So, as I showed, the group from Chinese Academy of Science Institute of Physics investigated hafnium, zirconium. We investigated titanium, scandium, magnesium. It's not published yet, but I can say the preliminary results. As well, we investigated, the people investigated sodium hydrides, the insulating, potassium hydrides, insulating, rubidium, cesium are both form of polyhydrides, but they're insulating, insulators and semiconductors. Strontium forms semiconductors, barium forms metallic superhydrides, but with very low TC, about 20 kelvins. So in fact, the island of superconductivity is very small and very narrow. That's the main conclusion at this point. And just a few interesting binary systems left. One of them is cubic actinium H10. If you look at this part of periodic system, we can compare the maximum predicted or experimentally found the critical temperatures of superconductivity for polyhydrides, we can see that when we move from up to down, from scandium to actinium, the critical temperatures grows, maximum possible critical temperatures in these binary systems grows. Scandium H9 should have about 169 kelvins. Next is yttrium H9, 243, and next lanthanum H10, 250. So we expect to see higher TC for actinium H10 than it was found for lanthanum H10. Let's go now from right side to the left side. For protactinium, it was predicted protactinium H8 with TC 80 kelvins. The next compound is thorium H10. It was synthesized experimentally. Our group synthesized it, and 161 kelvins was found. And the next should be actinium, which should demonstrate higher TC than it was found in thorium. The same story for lanthanum. Again, for praseodymium hydride, almost nothing was found, no superconductivity, except maybe some small transition around 9 kelvins. Next compound is cerium hydride, 110, 120 kelvins. And the next is lanthanum 250. So we expect that because in the actinides, the TC are systematically higher. For protactinium, it's higher than praseodymium. For thorium, it's higher than in cerium. We expect again for actinium H10 should demonstrate higher TC than lanthanum H10. And actually, if you just put the actinium in any search system, you will find that every year people publish about 100 papers on this topic. So actinium is widely used element. And even actinium 225, which has a half-life about 7 days, is widely used. It's not a problem to find this element and to use element to study compounds of this element, especially because another isotope of actinium, actinium 227, has a half-life about 20 years. It's not a problem to work for several years with this metal if it's one time synthesized. And nitrate of this element, actinium 227 nitrate, is available. I don't know where it is. I tried to perform this project in Russia. It's available. It's not a problem to find 50 nanograms of actinium in the form of nitrate. The main task is to reduce this actinium nitrate to pure metal and to load this pure metal, about 10-50 nanograms of this pure metal, to the electric ducts. It's a completely bureaucratic problem because to do it, you need to have a lot of licenses, special documents. People want with stamps, a lot of stamps, lead boxes. You need to place it there, transport from one institute to another institute. So it's completely bureaucratic problem at this moment. In principle, technically, it's possible, it's doable, it's possible to solve this problem. Okay. In the next part of my presentation, I will talk about several important questions, such as what is the maximum critical temperature superconductivity hydrides can achieve, and we can achieve it. Is it possible to reduce the stabilization pressure while preserving superconducting properties of polyhydrides? And the practical questions, how to reach low temperature superconductivity, which elements to take for that. Hydrides can be described by very relatively simple theory. It's phonon-mediated superconductivity. It's a commonly used theory, so-called Barling-Cooper-Schutter-Migdal-Eliashberg theory, where we have only one important function for us. It's an Eliashberg function, which describes superconductivity in polyhydrides. And actually, not whole function is important, but only two main parameters. It's the electron phonon coupling coefficient, lambda, so-called, and the characteristic phonon frequency, characteristic phonon energy, which is called logarithmic frequency usually, omega log. And there are several models were proposed to get from these two parameters the final TC, the critical temperature of polyhydrides. It's a classical model of Allen-Dines, and recently it was proposed another model found by machine learning on the quite big amount of data, computational data. It was proposed by CN and co-authors and published in NPG Computational Materials in this year, 2022. So they modified Allen-Dyes formula, modified the coefficients to get better agreement with experimental results in polyhydrides, and they also developed simplified formula using, again, the machine learning. So both of these models, actually 3 models, I will use in my presentation to show how to get the maybe estimates for maximum TC achievable in hydrides. So if we know EPC coefficient, electron phonon coupling coefficient, lambda, and if we know the logarithmic frequency, we can get TC, critical temperature of superconductivity. Okay, let's start from statistical analysis of the dependence of logarithmic frequency on pressure. In this presentation, I will mostly use a statistical approach because already a lot of data were quite huge number of populations were performed. So we can just analyze them, put a lot of dots on this plot, and see that statistically there is a clear correlation between the pressure and logarithmic frequency in polyhydride materials and even in classical conventional Baron-Cooper-Schiffer superconductors, usually metals and ores. They're at the beginning. They're placed at the beginning of this plot. So you can clearly see that 95% of data is under a straight line, which can be described with this linear equation, linear function. And it means that in 95% of cases, when we increase pressure, we can get some benefit in the logarithmic frequency. In order to increase the logarithmic frequency, we need to increase pressure, and vice versa. Okay, it's very useful result, and I will use it in the next slides. On the next slides. Next step is upper limit for electron phonon coupling strength. In this year, 2 guys, it's Emil Yuzbashyan and Altshuler, published very important paper in the Physical Review B, it's 2022. They found that there is a clear theoretical limit for electron phonon interaction in any materials described within a Migdal-Eliashberg theory. They found that superconducting state will not be stable if the lambda is over 3.7. Here, I just would like to remind you that in materials, all previous experimental measurements for materials gave lambda less than 3. We do not know any conventional superconductor with electron phonon interaction coefficient higher than 3. And they found that actually 3 is close to the maximum possible lead. In fact, in their theory, they found that maybe in some cases we can reach 3.5, 3.7. So that's absolutely maximum possible lead. And there are several simple applications of these theoretical results. We can analyze again this lithium 2 magnesium H16. It's a publication in PRL, and I just copy-pasted the picture from figure 4 from this paper, and you can see that in this material, the lambda, this electron phonon interaction coefficient, should be 4 and should be 3.7. In this case, we can reach TC, according to the actors, we can reach TC above 400, even 350, 473, as I remember. Those temperatures were published in this paper. But in fact, we should stop. We should say stop at this moment and let's think. The main result of this paper concerns the pressure range 250-300 GPa, where the superconducting state will be thermodynamically unstable according to this publication of Yuzbashyan and Altshuler, because the limit for lambda is valid in this paper. So I think it's a reason why we should not maybe trust this publication. And now we can use this theoretical paper and the maximum possible lambda for conventional superconductors, Baron-Cooper-Schiffer superconductors, from 3 to 3.7, to investigate the critical temperature of superconductivity as a function on pressure. You can see several lines. I used the Allen-Dyes model and the recently proposed model, CE model. Is it correct? Yeah. C model, and you can see two lines, red and blue. And most of the experimentally found hydrides are below them, but the correlation is quite clear. If you want to get higher TC, you need to go higher in pressure. You should increase pressure. You should increase pressure. But you see that the experimental results are actually below the theoretically predicted line. So we are not so close. We should not be very positive. We should be a little bit less optimistic than the model give us. Those models give us data. Another approach is to use a correlation between the lambda and between the electron-proton interaction strength and the logarithmic frequency. You see the correlation is actually negative. In most cases, 95% of cases, it's a different calculation and experiments mix it together, and you see that when we increase the logarithmic frequency, the lambda coefficient is usually decreases, and vice versa. When we increase electron-proton interaction strength, logarithmic frequency usually decreases. So this negative interaction, actually negative correlation, leads to the situation like described in the classical Greek mythology in the book about travel of Odysseus. So ancient hero, and in one of episodes of this book, he had to pass between two monsters, Charybdis, it's a low pressure, and Scylla, it's a high pressure. So when we use these two optimistic models, two optimistic correlations for logarithmic frequency and for correlation between logarithmic frequency and lambda, we can get such plots, such parabolic plots. Left side is low pressures, where the problem is that we have very low logarithmic frequencies, so we cannot achieve high TC. In the opposite situation, at high pressures, due to this correlation, we will have a low EPC coefficient, a low coupling, a low electron-proton coupling. Again, we cannot reach high TC. So the optimal region is between them, which is about 150 to 200 GPa, where you see the maximum, according to new CF models, the maximum TC is about 300 Kelvin. So in principle, I think we can reach room temperature superconductivity, but it's really complex, and it's the end of this story. So platinum H10 is quite close to the maximum. You see it's 250. It's exactly this model, and we have maybe maximum 50 degrees. That's all that we can get from hydrides. Okay. So now I will go to the next topic of my presentation. I will discuss a little bit physics and interesting points in physics of superconductivity and polyhydrides. As all we know, the story of superhydrides began in 2015 when the group of Mikhail Yeremets and Alexander Drazov discovered this remarkable superconductivity in metallic superhydrides at pressure about 155 GPa. The TC may reach 200 kelvins. And in the consequent years, between 2015 and 2022, the people studied several questions like how small the resistance in the superconducting states of polyhydrides. They also studied the properties of resistance drop, this sudden resistance drop, and how it behaves in magnetic field with different frequencies and with different currents. And now I will show, but they mostly didn't pay attention about the normal state behavior of hydrides, and now I will show something interesting in this field. This is one of the first publications, this experimental publication made by Alex Drazov in 2015. It's a publication in Nature, and it's a sulfur hydride. We see that at high pressure in normal state, the behavior of sulfur hydride is more or less normal. It corresponds to metals. So at least they have, seems like this compound have a positive temperature coefficient of resistance. So resistance, as it expected, grows with temperature, along with temperature. Temperature increases and the phonons scatter the electrons, and the resistance also increases with this parameter. But the most interesting case is low pressures. After decompressed compound decreased pressure in the cell and found that there is a reverse sign of temperature coefficient of resistance at low pressures. We can see that firstly this first derivative of resistance becomes zero, and after that changes its sign. And now behavior of HPS is not metal-like, but semiconductor-like. It's very unusual for metals, and it's very unexpected. The behavior, the dependence is linear, and it changes gradually. There is no some sudden drops, sudden changes, no fluctuation, so it probably belongs to the sample. Recently, we found another example of such behavior in the ternary lanthanum-cerium hydrides. It's published on arXiv. This compound demonstrates a quite clear superconducting transition. The residual resistance is zero. But in one case, in the DAC 5, we decompressed this compound and found that again, this first derivative of resistance changes its sign. And at high pressures above 130, we have positive temperature coefficient of resistance. And during decompression to 104 GPa, we found that it changes sign and becomes negative. And it becomes negative here, and still linear, completely linear. If we try to apply classical theory based on Boltzmann transport equation to this case, we can find that actually this coefficient should be proportional to the electron-phonon coefficient, electron-phonon strength. In this case, it's transport, but it's usually very close to superconducting electron-phonon interaction strength. And in some particular points where this derivative goes to zero, it means that actually there is no electron-phonon interaction in this case. It means that the lambda should be close to zero. Electron-phonon interaction should disappear in this material, but it's absolutely inconsistent with superconducting transition, which is observed in polyhydrides, and usually it explains by electron-phonon interaction and by Barden-Cooper-Schiffer theory. So it's a very serious contradiction. I would like to point out again that it's very serious contradiction. And probably hydrides cannot be described as a normal metals, but should be described as strange metals and with using non-Fermi liquid series. Okay, let's try to use alternative explanation. Maybe it's just some, something happened with the sample, maybe several phases appeared, maybe phase transition. Okay, if we connect two resistors together, one resistor is this superconducting sample, we will see that the second resistor will give us residual resistance after superconducting transition, but no residual resistance in both cases. In case of lanthanum-cerium hydrides, and the same is for superhydrides. There is no residual resistance, so it's not a serial connection of resistance. Okay, next case is maybe it's parallel connection of resistance. There are three cases. Of course, one of compound is superconductor, should be superconductor, but the second compound may be metal, maybe insulator, and maybe semiconductor. In case of metal, both coefficients, both derivatives are positive, so the final derivative will be again positive, but we should explain negative derivative. In case of insulator, we will see only resistance of superconductor, and the same case is for wide gap semiconductor. And final case is a narrow gap semiconductor. In this case, the dependence of resistance is very nonlinear, is exponential, and when we use summation, we will not see a linear function, linear dependence of resistance on temperature, but we see exactly linear dependence here. It's just straight line, just plain dependence, no dependence of resistance on temperature. So in both cases, we cannot explain the phenomena which we observe. Again, this picture, this small picture, just demonstrates my logic. Just again explains it again. So for metals, we should see such plot can be described within a Bloch-Reuneisen formula. For superconductor, before the transition for classical conventional BCS superconductor, we should also see a metal-like behavior. But in hydrides, at least in HPS and lanthanum-cerium H9, we see the behavior which is completely different. completely different and very strange. So some strange physics that also was recently observed in the cuprates. In cuprates, a group from Institute of Physics, Chinese Academy of Science, recently published a paper, a work in Nature Physics in this year, 2022. They squeezed in a diamond cell this cuprate, which is one of the most two-dimensional cuprate known. It's bismuth, strontium, calcium, copper oxide, 2212. And they found that after compression, they observed similar changes in the behavior, similar changes in the resistance. Firstly, at low pressure, the behavior is metal-like in the normal state of this compound. But after compression, we see that TC significantly decreases, and at the same time, the first derivative changes its sign. First derivative of resistance changes its sign, and the compound goes to the semiconducting state. So it's a transition between the superconducting pseudo-gap phase and next phase is insulating phase in this cuprates. And I think it's very similar to something we observed in hydrides. I'd like to point out here that there are several publications by Yuzbashyan-Altshuler in 2020, 2022. He published and analyzed Uemura plot. It's a plot between thermal temperature and the critical temperature of superconductivity. And he found and several times underlined that hydrides are very close to cuprates and their properties on this plot. This Uemura plot unambiguously identifies superhydrides and cuprates as the closest neighbors. So we should remember about it. And we can even propose some qualitative phase diagram, which is for hydrides, which is very similar to phase diagram proposed for cuprates. We also can observe here several regions. It's definitely hydrides may demonstrate a thermo-liquid and a metal-like behavior in normal states. It's no doubts in that. But they also may demonstrate strange metal, non-thermo-liquid behavior. And as you saw, pseudo-gap behavior with negative first derivative of resistance. And of course, superconductivity region is also here. Okay, and I would like just to maybe speculate a bit about the possible mechanism, what may happen during the compression of hydrides. Just very briefly, we need to answer the several questions. And how do atomic hydrides turn into molecular ones when the pressure is reduced and the hydrogen is released? For example, we know that when we decompress lanthanum H10, it will decompose to some lower hydrides, such as lanthanum H3, and molecular hydrogen will go out and become an insulating phase. We can propose a very simple primitive mechanism that firstly, atomic hydride goes to molecular phase. After this molecular phase, decomposes to lower hydride with emission of hydrogen, emission of insulating phase. So it passes via non-thermo-liquid phase, after that semiconducting phase, and after that again composition leads to thermo-liquid metal, but with lower TC and insulating phase of hydrogen. In this case, some phonons in hydrogen sublattice may lead to strong interaction between two neighboring hydrogen. They form excited hydrogen molecule, and this excited hydrogen molecule lives for a short time, but places an additional scattering center, or maybe additional some kind of excital, we cannot call it, but some kind of excitation which also participates in the scattering process. It's very similar to the boiling of water. We can boil water and generate and decompose the liquid phase of water by these two methods. We can increase temperature, or we can decrease pressure. In our case, in the case of hydrides, we decrease pressure. We decrease pressure, and the water or hydrogen sublattice start decomposing. And after that, the situation looks like pudding with raisins inside. We still have atomic pudding, hydrogen sublattice, and it demonstrates some superconducting properties. But at the same time, there are a lot of molecular raisins, regions, maybe fluctuations, where the sublattice, hydrogen sublattice is already molecular. And these raisins can play, can be additional scattering factor and can maybe explain the unusual and abnormal behavior of normal state resistance in polyhydrides. There are some other interesting properties that need to be explained. It's, of course, non-linear behavior of resistance, and sometimes it's very linear, which is also unusual. For this thin H4 at 190, we observe these curves, and they are very reproducible, very well reproducible. We see it's completely linear between 150 and 300 kelvins, and after that suddenly changes and become non-linear. Similar phenomena was observed for cerium hydrides. We see here there is some wave, some hill on the resistance. This hill again cannot be explained within the Bloch-Grüneisen equation within the classical models. Another publication, Nature of Physics, Maria Inaga in 2016 published several cars for superhydride. Again, we see abnormal behavior of resistance at high temperatures. I would like to also point and indicate that there are several anomalies in the behavior of upper critical magnetic field in thin hydrides in H4, cubic modification 190 GPa. The phase diagram, magnetic phase diagram, is completely linear. There is no deviation, there is no flattening, deviation from the linear feed. And the same was found in by Sven Friedelmann from Bristol University. They presented several pulse magnetic field measurements for lanthanum H4, and the magnetic phase diagram for this compound is also completely linear, which is unusual. You can see I collected the data for all hydrides, and this plot is published in this paper, recent paper in 2022. We published in Advanced Materials. You see that for almost all hydrides, the magnetic phase diagram, known part of this magnetic phase diagram, is linear, but it was predicted that it should not be linear. It should have a flat part according to conventional Wertheimer Helton-Coinberg model. So it means that we, in fact, should increase the estimation for upper critical magnetic field at 0 kelvins and change this coefficient 0.69 to 1. And it means that upper critical magnetic field of many hydrides may be much higher than we thought before. And the last part of my presentation, I will finish soon. It's about rapid magnetic flux in polyhydrides. It was recently found, and it's a great discovery, in my opinion, made by Vasily Minkov and Mikhail Yeremin's group in Mainz. They investigated polyhydrides like H10 and H3S using a SQUID methodology, using a special SQUID, very small, tiny diamond annual cells, so very huge samples of polyhydrides. They found quite clear response in magnetic susceptibility in zero field cooling. And they didn't find the same response in the field cooling, probably because such samples, such hydride samples, have a lot of defects, and that's why the magnetic field just penetrates through the sample via such holes. Okay, but at the same time, these defects can serve as opinion centers and can serve as a memory centers. Actually, can demonstrate the memory, superconducting memory effect. And it was really proved by this group, by a group from from Germany. They used some kind of magnetic pulse in a superconducting state of hydrides. They did a short magnetic pulse. And after this short magnetic pulse, they were able to detect, using this SQUID, rapid magnetic flux in the sample. And this rapid magnetic rapid currents generated magnetic flux, which is much higher than the magnetic response detected without this pulse, detected in previous series of measurements using SQUID and zero field cooling methodology. And it's very convenient to investigate dependence of critical currents on the temperature in the wide temperature region in this in such superconductors. A bit later, maybe several months later, George Hirsch, or maybe several months before, George Hirsch published a paper that similar effect should be actually observed in voltage current characteristics and in critical currents. So he gave one example when the authors investigated EBCO and found that actually critical currents depends on the history of the sample. There is an obvious hysteresis loop, which depends on the history of the sample and depends on the question, was this compound before in the magnetic field or was not? So again, this picture demonstrates, this picture explains my logic and my idea. So if there are sharpened magnetic flux in the sample, it should change also the critical current which passes nearby these centers and close to the centers. So we should see the similar effect as Mikhail Yeremets and Vasily Minkov saw in the SQUID measurements, but we also can see it in voltage current measurements. If we measure the critical current, the trapped magnetic flux should affect on critical current and should decrease. Okay, we did this experiment, and it's partly described in this publication, Advanced Materials. We used this pulse magnetic field diamond angle cells with the sample. It was lanthanum H10 doped by neodymium 6.5%. The sample demonstrates some superconducting transition, quite narrow transition, about 8 kelvins. And below 154 kelvins, we can do transport measurements and measurements of critical currents. You can see it here on the next plot. The critical current in the sample about 150 kelvins is 9 milliampere, where we can see the voltage appear. After applying such current, 9 milliamperes, the voltage appear and the sample start to behave as a normal metal according to the Ohm's law. Okay, in the first experiment we just made the same pulse as was done in mines. We just switched on field and switched off field. And after that, after degaussing of the magnet to remove the residual magnetic field, we measured again this critical current and found that there is a hysteresis loop. And the critical current is now much smaller. It's a 7.6 milliampere instead of 8.4 milliamperes. Okay, we repeated this experiment in a different manner. We cooled the sample in magnetic field. It's a field cooling in 1 Tesla. We cooled the sample firstly without any field and measured the critical current at different temperatures. And we repeated the experiment several times, so that's why you see several curves here. They are very well reproduce each other. It's not a problem to reproduce it. And after that, we switched on field, cooled down the sample, switched off field, and temperature raised again to 153 kelvins or 151 kelvins, and measured critical current again. And with several times, we were able to reproduce the fact that critical current is now different, and the sample remembers what happened, remembers the field that was applied. So the polyhydrides definitely demonstrate the superconducting memory effect in these measurements. We confirmed this fact. And after that, we also studied the dependence on applied magnetic field. And we again found that the critical current is significantly suppressed if we used higher magnetic field. We investigated 3 fields at this. It's a 10 millitesla, 50 millitesla, and 100 millitesla, and found that in the field cooling mode, after switching off the field, the critical current is proportional to the field applied. Correlation is negative, and you see that the higher magnetic field suppresses strongly suppresses critical current that can be found after such procedure in the sample. So we confirm the temperature dependence and magnetic field dependence of this superconducting memory effect in the polyhydride samples. Okay, that's all. I just would like to remind and make several conclusions. That's all that I wanted to say. The most important points of my presentation is that the most promising pressure region, as I told before, for achieving room temperature superconductivity is probably between 200 and 300 GPa, a little bit higher than people usually use. We should not trust a lot to the papers which violate Yuzbashyan-Altshuler limit for conventional electron-phonon interaction described within Migdal-Eliashberg theory. The limit is 3.7, and if we see the paper with 4, 3.7, it means they're probably not reliable. I would like to again say and repeat that island of high temperature superconductivity is extremely narrow. We have only very narrow choice, about 4 or 5 elements, what to do and how to construct ternary systems. We can use calcium, yttrium, lanthanum, thorium, maybe actinium, but it's quite complex, and H3S and maybe cerium hydrides. That's all that we have. Actually, it's very rare phenomenon. High temperature superconductivity in polyhydrides, it's very rare phenomenon. We should think about strange behavior in normal state of hydrides, especially resistivity. And maybe we should start to think about how to build the superconducting phase diagram for hydrides. And should it be similar to the cuprates or should not be similar? And finally, we found in our work that voltage current measurements are very useful and maybe used instead of SQUID measurements because they are much simpler. You can do it in the same cell where you measured standard resistive transitions, where you studied its dependence on magnetic field. And the next step may be measurements of these loops of critical current in different conditions to confirm that there is a trap in magnetic flux, to confirm that there is a Meissner effect in polyhydrides. And I hope that in Beijing HPSTAR, I can also study my cerium sample in the same manner to confirm this, to confirm the first measurements done for neodymium doped lanthanum H10. So thank you very much for your attention. That's pretty all.
Thank you very much. Very nice talk. Very exciting. So questions from audience?
Nobody tries to question? Can I ask first question maybe?
Okay, welcome.
Very impressive talk, thank you. And regarding your model about optimum TC in hydrides, you have anti-correlation between lambda and average logarithmic frequency. It's kind of not really a dependence, it's rather a trend, right? Can you comment on that? Because
it's a statistical result, Victor. It's a statistical result. I just collected a lot of data and compared what people predicted. Yes, it's a result that calculations give us.
So yeah, so I wanted to comment here. As any statistics, there could be outliers, right? So the curves you later calculate, there could be some systems which jump up in TC.
Exactly. Yes. There is always probability of that, and but we should not exclude the possibility of errors, some errors in calculations.
Yeah, but I just wanted to double check that it's not something I missed, and it's a statistical thing. Maybe a second question regarding this. This paper by C et al. I actually missed it. What's important development they did there compared to Allen and Dines?
In 1975, the hydrides were not known, were not discovered yet. So they added modern data, modern experimental data, and a lot of also DFT calculations results to their analysis, to their statistical analysis, and reanalyzed experimental or results.
So basically, they used the same logic as Allen and Dines, just
yes, but a little bit more modern because they used machine learning, so it was some kind of neural network.
I understand, yeah. So current methods too. I don't like machine learning, but apparently it's going to be here with us for quite a while, so we'll see. Okay, thank you very much for your answers. Yeah.
Okay, thank you, Victor. I would like just to add the comment that I checked these formulas, and I found that for hydrides they give better results than the Allen Dines. For hydrides, they give much closer to see to the experimental.
Yeah, I understand. It certainly should because they were designed for this. Yeah.
Yeah, of course.
Maybe a naive question. So when you say that there is a maximum for the electron phonon coupling and the TC, right?
Yeah.
Why? I mean, naively, I would have thought that high electron phonon coupling is actually good for TC, right?
Yes, definitely good.
So, but why should there be then a maximum in lambda?
The problem is. I
mean, I haven't read the paper yet, but
yeah. the problem is that we have two parameters at the same time, and they have negative correlation between each other. In such situation, it always will be parabola. Actually, it's not only one case of superconducting hydride. So we have two parameters: it's logarithmic frequency and lambda, and you see that when the lambda increases, TC increases, but at the same time, logarithmic frequency decreases statistically, and again the TC decreases. So final result is this parabolic.
It's more like a compensation through the logarithmic lambda. I see.
Exactly. Yeah.
Oh, interesting.
Between hydrides and Scylla, you need to pass between these two monsters.
And have you? I mean, there are a couple of calculations on ternary hydrides of a land filament yttrium. Have you tried something like that at some point? I think D, you said at some point that you tried it.
Yes, it's already published in previous year, 2021. We're publishing materials today, and the result is the TC almost the same as Coulomb H10. So you can add yttrium, and it will be in the same configuration, in the same structure. It also will be cubic and Humphrey structure, but unfortunately the TC is almost the same.
Yeah, okay.
So no changes.
Oh, I see.
No improvement.
Oh, that's weird.
The maximum we have is H18 is not H10.
H18? No, it's the same.
Ah, I see. Okay.
Okay, I have some question for you. It's a very interesting you raised a question about this stringent resistivity resistance behavior just above the TC. You found a linear relationship between the temperature and the resistance. And also this is already very famous question in cuprates, there's a stringent metal region. On the other hand, you mentioned this TC is very strongly dependent on the electron phonon coupling. Seems this is a little bit a dilemma here because the BCS theory is not suitable for cuprates high temperature superconductors. So, yeah. So, what's your opinion? This is a BCS type or non-BCS type, according to your experience?
According to my experience, it's 90–95% that this is BCS-like theory, Miguel-Eliasberg BCS theory, and the main mechanism is electron phonon, of course, coupling in hydrides, but the behavior in normal state is not metal-like and cannot be described within the Fermi liquid theory. That's a big difference. So in this case, we should apply different theory, and Fermi liquid cannot be applied. It's wrong. It's wrong to describe the normal state of hydrides. But of course, the transition is still electron phonon mediated superconductivity.
So how about the constant resistance in some region, the differential of resistance to temperature to 0? So
yeah.
why that happen?
Interesting. It means there are two factors. One gives a negative contribution to the derivative, to the first derivative of resistance, and the electron phonon interaction gives positive contribution, so they somehow neglect each other.
So what could be the negative effects on this? Well, some competition effects, right?
Yeah.
There's pressure-induced band broadening or delocalization or whatever it is, like free electron, but there's some counterpart effects there. Could it be disorder or maybe structure frustration? Any comment?
At this moment, I cannot say anything about this. It's just some anomaly that need to be explained. We need to pay more attention on that. That's why I just want to attract to maybe focus on the on this phenomenon, because no one before actually tried to explain or tried to discuss it, at least in hydrides, but it's definitely something absolutely abnormal, something absolutely unexpected.
Okay, I have another question regarding this BCS theory. I'm not sure if you noticed one paper published in 2016, which is measured on the lanthanum surrounding cuprates. They find that the TC is strongly dependent on linear changing with the superconducting electron carrier density. So from an electromagnetic dynamics aspect, seems it's not really dependent on the proton electron coupling. So now I think all the theory prediction is strongly emphasized on the electron photon coupling only, but it looks in the reality, the electron dynamics parts, which is how the electron are moving this superconducting states, probably is also important. Do you have any thoughts?
No, unfortunately, cannot comment because I didn't read this paper, and I'm not sure. I'm not a specialist in cuprates, so hard to comment for me. Sorry.
Okay, thanks.
Thank you for your questions.
When you, I mean, for those hydrides, we all have band structures, right? Electron band structures.
Of course, we have. Yeah.
Have you tried to have a look at the
yes,
at the Fermi energy?
Yeah, we tried to analyze
and just plot it against temperature.
Yeah, it's against temperature. It's exactly this plots. I will show it. Yeah, this is done by Talasov.
Yeah, okay.
It's exactly we made a plot, and you see that all hydrides actually belong to unconventional superconductors, to the region of unconventional superconductors very close to cuprates. That's why I just made a direct analogy between the cuprates and the hydrides and built the same quantitative phase diagram, superconducting phase diagram that I showed on the next slide.
I see. I mean, the phase diagram might be like, might look completely different, but
we have several reasons why it's maybe not completely conventional superconductivity.
Yeah,
but 1995, I still believe that this is.
But I think you're not the only one saying that, right? I think like Hirsch also suggested that it might not be.
Yes, at several first publication, he suggested that it's maybe unconventional superconductivity, but later he just stated that it's not superconductivity.
Yeah, at all. Yes, I know. Yeah. Okay.
Some more questions? Oh, okay. I have an additional question regarding the flux trapping measurements. You basically measure this magnetic magneto resistance, right? You're changing the magnetic field, you change the resistance, and based on the resistance changes, you can try to say there's some magnetic expulsion happen in the sample, right?
No. We didn't measure resistance. In this case, we just directly apply the current and measure voltage. So actually, no resistance here.
What was the magnetic field pulse?
Magnetic field pulse? You mean in this case?
No. With the flux trapping, you said that you are
flux trapping. Yes, this one. Yeah.
This one.
Right.
So it's classical voltage current diagrams, voltage current plots. No magnetic field. In this case, in this plots, magnetic field is 0. So no magnetic resistance.
I mean,
so how can you do this measurement? I'm trying to learn the details. So you wanted to measure this flux trapping, right?
Yeah, exactly. And I want to the main idea is to measure critical current for fixed temperature and fixed magnetic field. In this particular case, fixed magnetic field always zero Tesla. So after the Gaussian of the magnet, it's 0. And after that, we just check, does the sample remember what happened with him before, or does not? So the sign is exactly the value of critical current when this plot start to increase when in fact, the voltage appears on the sample. It means the resistance also becomes non-zero.
Right. I think you just applied, you measured this resistance before the magnetic field applied. Then turn on the magnetic field and turn off magnetic field, then measure the resistance again, right?
Exactly. Yeah,
so,
right.
so why don't you test the memory of the of the sample to the magnetic field, right?
Right. Mm-hmm.
Okay. So you see this hydride loop here.
Exactly. Exactly.
So
Yeah.
this is a unique, conclusive measurement for the Meissner effects. Is there any other possible reason for this kind of hysteresis?
Of course, we didn't analyze in details what's possible reason of that, but we were able to repeat this measurement. So we tried to do not apply any field, and we were able to repeat and confirm that actually it's repeatable type of measurement. So the same critical counts were obtained for many cycles of cooling and heating without magnetic field. And it definitely depends on applied magnetic fields in the history of the sample, I mean, in the past of the sample. So when we apply small magnetic field, the memory is very weak. But when we apply a higher magnetic field, the memory becomes stronger and stronger. So it depends on the history. It depends on the past of the sample.
Okay. Thank you very much.
Thank you. Thank you for your questions.
Any question? Leading, do you have any question for?
Yeah, a very nice talk. I follow Yang's question about the traffic magnetic flux measurement. This is very important experiments because for this type of the sample, it's difficult to do very obvious AC susceptibility measurement, the results from the AC susceptibility. But if you measure the resistance versus temperature, and then you extracted IV curves, so you see the loops. That's a very nice results. And actually, we did the same measurement for our sample, but I don't know why we cannot see the loops. I don't know what's the reason for that. Perhaps we can have a detailed discussion when we met.
I may try to speculate a bit about this because this effect depends on the number of defects in the sample. If the sample doesn't have enough defects, of course, you will not see any effect, any such hysteresis loops in the current measurements. Because the hydrides, it's specific properties, specific property that the number of defects is extremely high. It's a very defective sample. That's why the field cooling measurements usually fails for in this magnetic susceptibility measurements. It usually fails. And it was also found for magnesium diboride, some of the magnesium diboride samples, very dirty sample, polycrystalline samples, and so on. And only in this case, you can measure the trapped magnetic flux, which is quite high and measurable. So I think this is one of the reasons, because for cuprates it was measured. It was such hysteresis loops were published in not in only one this publication, but several publications are given even in this paper of Hirsch, and I think we can find more publications about cuprates and hysteresis in them.
All right. And another question is about the phase diagram. Can you go back to the phase diagram? Yes, this is very interesting and also very impressive, the phase diagram. You think the superhydrides are very similar to the cuprate. So when we right?
Continue, yes. Yes, I think they are very. They may be similar, but
Maybe similar.
yes, but maybe mechanism is different. The mechanism of superconductivity is different, but the same. The phase diagram is somehow similar because what's a distinguishing feature now for strange metal behavior of cuprates in normal state is linearity of resistance in a wide temperature range. And in many cases for hydrides, we also see unusually linear behavior, unusually linear resistance dependence on temperature dependence on resistance in wide temperature range. That's why I place so big region for strange metal behavior and non-thermoelectric behavior of polyhydrides here as well.
I see. So why do you say on the left of the phase diagram is the photo gap like stay there?
Yeah, it's exactly the case we discussed when the superhydride or lanthanum hydride have a negative temperature coefficient of resistance. It's a semiconducting-like behavior, and actually, first principle calculation or ab initio calculations also show us that in some of the superconductors, such as barium H12, this pseudo gap should be observed. It's obviously can be calculated, and the calculations seems like correspond very well to the experimental observations as well. So it should exist. It should exist according to the calculations, and we found the first signs of pseudo gap phase in the H3S and the lanthanum polyhydride as well.
I see. Okay, thank you very much.
Thank you for your questions.
Any more questions? From Shanghai, from Changchun? No more questions? Okay, if no more questions, let's thank Small Nook again for very nice talk. And I will see you next month. Also, New Year's begin. So if you have any comments and suggestions how to make this interesting group talk better, just let me and Victor know. We'll try to do our best to make it better. Thank you very much. See you next month.
Thank you very much.
Thank you. See you all.
Goodbye.
Bye-bye.